3, titled Energy, is divided in two parts: energy resource and energy model implementation. In this chapter, we are going to take a quick look at the great importance of energy in the development of humanity and of societies, the current stagnation in oil production and the peak oil concept, the ROI, or energy return on energy invested concept and its importance, the current situation of other non-renewable energy sources, and the challenge of renewable energy sources for filling the gap left by the other energy sources. The figure shows the history of energy transition for almost 200 years. Wood, a biomass, was the first source of energy. With the Industrial Revolution in the mid-1700s, coal began to replace biomass as the primary source of energy. The massive use of oil and natural gas didn't start until the early 1900s, when large reserves were discovered, and this process has intensified since the end of the Second World War. The most important observation is that energy transition on a global scale is additive and not replacive. Energy availability has a powerful influence on population growth. The figure shows how growing amounts of available energy have boosted the number of people on the planet. Also, on economic growth, there is a correlation between global energy consumption and global GDP, or gross domestic product, growth. Energy change comes first. But now we have a problem. As I said before, population and economic growth depend on the energy availability of all energy sources. And the main one, oil, is showing signs of exhaustion. Between 2004 and 2015, the total production of crude oil plus condensates has moved around a band of 5%. The International Energy Agency announced in November 2010 that conventional crude oil production peaked in 2006. But what is peak oil? Peak oil is the theoretical point in time when the maximum rate of extraction of petroleum is reached, after which it is expected to enter terminal decline. The concept of peak oil is often credited to M. King Hubbert, a geologist who worked for Shell Oil and for the USGS. He predicted a peak oil production from conventional oil fields in the lower 48 states and near shore waters to occur in the 1970s. This did, in fact, occur, and subsequently his forecast for both US and global production gained a wide audience. The Hubbert forecast was made after many decades of production using a database compiled from a major producing company. Hubbert had access to a reasonably complete knowledge for each region's geology, production techniques, and production history. Because a similar knowledge base for the entire world does not exist, it is more difficult to forecast global peak oil. In the figure, we can see different predictions of global peak oil for the sum of conventional and unconventional oil. But conventional oil is not equal to unconventional oil, as they are not valid for the same purpose. For example, tight oil, which is a kind of light oil, is not good for making middle distillates, like diesel and jet fuel, and also because of their energy content and their cost of extraction. In the figure, we can see the cost of extraction and the share of the different types of oil that are currently being exploited. There's less and less cheap oil left. The cost of extraction is also related to ROI. Energy return on energy invested, or ROI, is the ratio of the amount of usable energy delivered from a particular energy resource or energy collecting system to the amount of usable energy used to obtain that energy resource or to build, operate, and decommission that energy collecting system. Arithmetically, the ROI can be defined as in the figure. This figure shows an illustration of the life cycle of an energy collecting system or energy resource divided in three stages: 1, construction; 2, operation; and 3, decommissioning. Energy inputs, in red and yellow, occur at each stage, but energy outputs, in blue, will normally only occur during the operational phase. The ROI which is the net amount of energy left to society, is better the greater it is. In the figure, we can see how the oil liquids that we currently exploit leave us less and less available energy. And since oil is going to supply us with ever less energy, the key question is if any other source of energy can compensate for this loss. As we can see in this graph, nuclear energy does not look like it is going to increase substantially. As with the concept of peak oil, there are peak uranium, peak coal, and peak gas. And as we can see in this figure, the predictions for peak uranium are similar to those of peak oil. And as we can see in this figure, coal does not look like it is going to fill the gap left by oil because there are big problems for it to continue growing. Neither are the predictions for peak coal any good, as we can see in this figure. Gas is the only energy source that is still growing, but for how long? Most predictions are similar to those of other fossil sources. The peak will be reached in a few years. As we have seen, problems of fossil fuel supply could well occur in the short term, and the key question is whether renewable energies can fill the gap left by fossil fuels. This is one of the main questions to be answered by the MEDEAS model. We face the great challenge of electrifying most of the economy and match it with the time frame of the decline of fossil fuels. The task is not easy because the current deployment of renewable energy is mainly to produce electricity, and the share of fossil fuels in world primary energy demand is currently 81%, while transport accounts for 29% of the total world final consumption. We are now developing and exploiting renewable energies using fossil fuels. In the future, we will have to do so using electricity. Most renewable and non-conventional energy alternatives have substantially lower ROI values than conventional fossil fuels. Not all sites with a high renewable resource potential are likely to be used because they must be technically and economically feasible, and we cannot afford to repeat the environmental mistakes of fossil fuel exploitation. These last two questions, the ROI and the potential of renewable energies, will answer the question of what energy levels society can eventually enjoy. First, we have the theoretical potential, which is the amount of renewable energy output derived from natural and climatic conditions, for instance, the total solar irradiation on a continent's surface. The geographical potential is the second highest level, which depends on the limitation of the geographical areas, such as mountains, glaciers, urban land, etc. The technical potential is the amount of renewable energy output obtainable by full implementation of well-proven technologies or practices. The economic potential is the technical potential when costs and benefits are included. And finally, the sustainable potential is when long-term environmental development is not hindered. In this chapter, we have described the direct correlation between energy and population and between energy and GDP, the peak oil concept as the time when the maximum rate of extraction is reached. This concept can be generalized to other energy sources, the importance of the ROI and its value for different oil types, the current stagnation in oil production, coal and nuclear energy, and the doubts about future gas production, and the great challenge facing renewable energies to fill the gap left by fossil fuels. The next part will show how energy sources are modeled in MEDEAS.